Nonstandard bases. In this lesson, we discuss nonstandard bases and change of basis operators. Up until now we've performed transformations on the standard basis, with unit vectors along the coordinate axes. It's often useful to use a different vector basis, which is physically meaningful or just mathematically easier to work in. As an analogy to a vector basis, let's consider two hypothetical cities. City A is laid out in a uniform grid with streets running north and east. City B is laid out with streets running for the most part north-northeast and east-northeast. Furthermore, the blocks of City B are noticeably longer than the blocks of City A. To be more precise, if one were to walk for a block of City B, from one intersection to the next, along one of the more easterly running streets, in City A's layout, one would have to walk 2 blocks east and 1 block north to reach the same position. And, if we walked for a block of City B along one of the more northerly running streets, in City A's layout, we would have to walk 1 block east and 2 blocks north to reach the same position. Each city has a natural basis which makes it easy to navigate that city's geometry. City A has the standard basis 1, 0 and 0, 1. In terms of the standard basis, City B has the basis 2, 1 and 1, 2. Suppose we are in City B and we want to go from point 1 to point 2. We would walk 3 blocks in the easterly direction, turn right and walk 1 block in the southerly direction. We can write this vector as a linear combination of City B's basis vectors, 3b1 minus 1b2. In terms of the standard basis, it is 3 times 2, 1 minus 1 times 1, 2. This gives us 5, 1, the directions we would follow in City A's layout to get to that point. Notice that we can write the linear combination 3 times 2, 1 minus 1 times 1, 2 in matrix vector notation. The matrix M is a change of basis transformation, which changes the basis from B of City B to the standard basis of City A. Once again, M changes the basis from B1, B2 to E1, E2. Since the inverse of an operation undoes that operation, the inverse of M will change the basis from E1, E2 back to B1, B2. For example, consider this vector in the plane. Using the standard basis, this vector is given by 5, 4. Applying M inverse to this vector will change the it from the standard basis to the basis B1, B2, which happens to be the vector 2, 1. Let's return to the sheep. In the standard basis the transformation, 2, 0, 0, 1, stretches the sheep by 2 in the x direction. But what if we are instead using the basis B1, B2? What matrix operator in the basis B1, B2 will produce the same effect of stretching the sheep by 2 in the x direction? We will break the solution of determining the matrix B into 3 steps. First, apply the matrix M which changes the basis into the standard basis. Now that we are in the standard basis, apply the matrix A. This will stretch the sheep. We need to go back to our basis B1, B2, so we apply the change of basis operator M inverse which takes us from the standard basis to B1, B2. The matrix B equals M inverse, times A, times M. The matrices A and B are called similar matrices. They represent the same geometric transformation, in this case, stretching by 2 in the x direction, for 2 different bases. Note that we can also express A in terms of B. This time we've taken our standard basis and converted it to the basis B1, B2. This procedure, called a similarity transformation, is a useful way of simplifying a problem by using the natural geometry. In a good basis, the matrix may be as simple as a diagonal operator, which simply stretches in the direction of the basis vectors. We'll return to this idea of matrix diagonalization when we use eigenvectors of a matrix as a natural basis. Let's close this lesson with an example of using the matrix 7/3, minus 2/3, 2/3, 2/3. This matrix happens to be similar to the 2, 1 diagonal matrix. This means that there is a basis on which the 2, 1 diagonal matrix behaves the same as the original matrix does on the standard basis. The basis happens to be 2, 1, 1, 2, the basis which we associated with City B. Now we have 2 equivalent interpretations of the triple product. The first is 3 consecutive operators. The second is a change of basis from the standard basis to the new basis, stretching by 2 and 1, respectively, in the direction of each of the basis vectors. Finally, changing our basis back to the standard basis. Let's apply these operators one at a time. We apply the rightmost matrix first. On the left, we sheared the sheep. On the right, we have changed the basis. If you closely examine where the underlying grid crosses the sheep, you'll see that both pictures represent equivalent transformations. The next operator stretches everything by 2 in the direction of the first basis vector. Nothing changes in the direction of the second basis vector. On the left in the standard basis, we stretch the sheep in the x direction. On the right, in the new basis, we stretch the sheep in the 2-1 direction. Finally, we apply the third operator. This changes the basis of the system on the right back to our standard basis.